So hi James, how are you doing?
Doing well, thank you.
That's great. So yeah, let's get started with the presentation.
Sure. Okay. Um, so I'll go ahead and start with the presentation. Today's talk, I'll talk a little bit about engineering system on chip flows for SkyWater 130 nanometer Open PDK, and it's a great honor to be here. Thanks to all the help, Stefan, for all this help in getting this going. My name is James Stine. I'm with Oklahoma State University, and talk a little bit about what we're attempting to do here. And it's an ongoing effort. So the outline of our talk today is to give you a brief introduction, followed by talk about the SoC design for SkyWater 130 nanometer. We'll also give you a little bit of a standard cell review, followed by a brief conclusion. So I've been very fortunate over the years to have really wonderful graduate students. These are a picture of my current graduate students in front of our Endeavor laboratory, and they've just been indelible and just wonderful in helping in this process. They've helped throughout the whole project, and they're continuing to help. They've gone above and beyond, and they're just all extremely talented students. I'm very grateful to have them all. I just wanted to acknowledge them before I go forward, as well as my former students who've just also been outstanding in what we're doing. So who are we? We've got almost more than 25 years of experience designing standard cells. We've done them for Moses, the free PDK, EDA companies, as well as other academic pursuits. Our main area of research in what we do is computer arithmetic and architectures. But when I first started out, I really didn't have any method of trying to do this process of getting results. And so I was really at I would say, a conundrum. What do I do? I tried contacting a lot of companies to get the process of getting libraries and design flows, and it was just very difficult illegally at the time. This was the late 90s. Along with a lot of my many talented students, we started designing SoC design flows to really help alleviate this problem, as it was really difficult to acquire these standard cells and IP from companies. And so, because a lot of people have helped me along the way, our goal is really to help others in learning how to work and create these design flows. And we've also had a strong history of designing design flows and IP and memory and architectures. We've designed, again, the cells for Moses. We're using the scalable CMOS rules, which are listed here. I also developed the standard cell libraries for the free PDK 45. That's along with my good colleague, Brett Davis at NC State. And that was really successful and a lot of fun. I also helped co-developed one of our initial NSF-funded OpenLANE projects with Professor Matt Goodhouse at University of California, Santa Cruz. And he currently leads the movement of continuing that effort of providing open source memories. It's sort of a segue into the next presentation. He'll give an idea of using OpenRAM, which is a great tool for generating memories, as is another open source type tool. I've done cell libraries, IO pads, memories, and flows for Cadence, originally in the GPDK. I also designed memories and cell libraries and flows for Synopsys and Mentor Graphics, as well as designed cell sets for the Air Force Research Lab up in Rome, New York. So I'm very grateful for all these opportunities, as we had many other opportunities as well along the way. So our goal really, again, is to help others with the process of designing and exploring the wonderful area of system on chip design. And we're trying to use our experience to sort of take the next step. And our idea is to create an alternative standard cell kit with the pre-existing SkyWater cells. And the idea here is that we will do everything from scratch and provide everything that we possibly can, including scripts, libraries, examples, design flows, to really, show this exciting area and allow others to collaborate and work with this design. And as I all said, maybe in other avenues, we have a Slack channel related to this, and we have an OSU Slack channel on that, SkyWater PDK Slack.com. And you're welcome to ask questions, ask for ideas, ask for requests in relationship to anything that we're trying to work on. And we're always very open and really welcome that collaboration. We really love this area, and we really want to help you as well as maybe you can help us at the same time. So we're sharing our knowledge with the standard cell design so others may be able to create their own cells. Again, we're providing all the scripts, all the source files, all the ideas that we did. They're always a work in progress as we go. So as I'll talk about today, we have updates to those cell sets that we're continuing. We should get another release out in 1 to 2 weeks. And we're continually doing that as we go. And the website is listed here. And if you forget that website, you can always contact me, either email or Slack channel or something like that. So the SkyWater 130 nanometer PDK also has some standard cells. They're listed here, and they have various cell heights, 9 tracks to 7.35 tracks. They also have several threshold voltages that they utilize to sort of target certain types in what they're doing. These cells only provide 5 combinations out of a really dozen of possibilities. And all the columns in the table are design parameters that can be adjusted independently, meaning there's really far more opportunities for these cell sets. So why do we want to do something more? Well, we wanted to create something that was everything that was there, using all our knowledge that we've done before in designing standard cell libraries. And we've done standard cell libraries and designs for various different technologies, from very high levels, 1 micron, all the way down. We just taped out 14 nanometer for a design over the summer. So we have a lot of experience in doing all these designs in silicon. And we really wanted to use that knowledge to provide a standard cell and SoC design kit that was really helpful for others to use. And we also wanted to do a design that was not defined by log wires and high logic fan out. So we wanted to use taller cells that would be a better fit than the current SkyWater standard cells. We have high density cells that are only offered in really one single flavor, but we're always looking to tune this out, and I'll talk about some of the other flavors that we're currently working on, as well as the customizations. So the SkyWater standard cells are different. They do not have a built-in substrate contact. Ours do, which minimizes the body effect for those that are interested in MOS transistors. The routing philosophy that we try to use is we try to restrict the cell routing on the really high resistance layers, and the thicker power rails are utilized in order to prevent electromigration. And all these small details add up in changing a product that we can actually put out that we can help others with, as well as all the scripts that you could potentially add stuff to or potentially enhance in any way that you would like. So due to the initial issues with the modeling, we designed our base set cells around an 18-track height, which is about 6.66 micron. There's currently 62 cells in the library, and as I said before, we're currently always adding more cells as we go. And our goal really is to create the best possible cells through repeated iterations and refinements. And as I said before, we're always looking for feedback and always looking for people to help out. So all the files and scripts are provided. We try to provide those as much as possible. And if you're confused about something, you can always contact us in the Slack channel. We'll be happy to help. The design flows are also provided to allow others to use the cells with an SoC design in mind. So this currently shows the ideas of what we're putting out. We currently have an 18-track cell set, which we show towards the top of the table. This is already completed. It's already out there on the Google site. We also have a couple other cell sets, 15 tracks, 12 tracks, 9 tracks. And we also are going to do different speeds, high speed, low speed, power type of conserving types of cells. And we'll put those out probably very, very shortly. We already have them done. We just have to do some of the characterization on some. And then some are also in progress. And we do expect those to come out within maybe a week or two. So we're always consistently putting those out. If you ever are curious, you can always ping us and we'll tell you when that we'll put those out, or we can even ping you when we put them out. So system on chip involves an idea, and you're going idea to silicon. Sometimes people say idea to GDS, and you're going from a schematic to a layout, and then those layouts also have SPICE models, timing libraries, and they also have specific views, which we call left views, that also provide area measurements, timing measurements, which are aiding in synthesis with the timing libraries to generate a place and route, which is our final GDS. So we're going through this formal synthesis flow, which is a forward progression flow of IC design. And we typically call this an SoC, or system on chip design flow. The standard cells that we design sit at the base of all good designs. And so that's what our ultimate goal is. And so we always know without good standard cells, you can't make a good chip. So our main goals are on the kit are to minimize the area and power consumption, while trying to maximize speed, at least for the 18-track version that we have, and then for the coming ones that are coming out very, very soon. Each of these, of course, comes at a cost of others. Of course, you can't get the total speed without a lot of power and so forth. And so you must sacrifice some of these to sort of meet the other types of constraints that are there. But all these cells are there so that you can see those in action. And we're extremely excited about what we can do and the options that we can do in this realm. Many standard cell kits are commonly provided with multiple versions of each cell. So this is optimizations that we can do for power. And so we're looking at changing the threshold voltage, and then we're looking at intermixing them with a single design. And we hope to have those out extremely shortly. And we can use those to trade power and speed for the scope of our design. You could use IEEE 1801 constructs, which is now part of the Verilog standard. And our main goal is to providing the ability to implement SoC designs, as well as provide files that others can use and hopefully contribute back to the project. So for the layout, we use Magic, which is a great open source tool actively maintained by Tim Edwards at eFabless, who's been really outstanding. And we're very thankful for his efforts as well as his help over the years. We prefer it over commercial tools for our research, and we've written tech files for the Magic program. It's really a great tool, and that's why we're using this for our layouts. All the source files are given. The website for downloading Magic is shown here for any of those that are not familiar with it. And it's a really fabulous and easy tool to use. Again, it was written originally by John Alsterhout, but it was really taken to a new level by Tim. And he has just gone to extraordinary lengths to make this a really fantastic tool. So Tim Edwards is also part of the 130nm Open PDK project, and he frequently makes updates to them to meet the needs of this project. And again, we really use Magic, especially in our classes here at Oklahoma State, originally for scalable CMOS, but now we're migrating to the 130nm Open PDK, and there's a Magic tech file for the PDK that will be included as part of the general release. So anybody, anyone, anywhere can start creating layouts from day one, which is really the whole idea. We also have SPICE models associated with the PDK, and that always is useful for the Magic to extract the baseline SPICE model, and then we can use that to simulate. All our cells are parasitically extracted, which we typically use the acronym PEX, and all the PEX is done with all the cells for good resistance, capacitance, and any parasitic devices in a three-dimensional type of design. Right now, we currently use Calibre for Mentor Graphics to perform our PECs, but we hope to maybe hopefully do an open source type of PECs down the road. And this gives us a really better model to see how the cells behave, especially as we do simulation, as we'll see a little bit later. The SPICE can be used to accurately simulate our cells in a variety of conditions. And the OpenPDK has been really hard at work at trying in the last few weeks of the release to really try to provide a great SPICE model so that you can simulate. And here's a sample simulation that we have from our cell sets. And it's compatible also with open source type of SPICE engines. Of course, the original SPICE engine comes from Berkeley, but there's other versions out there, including the ngSpice, which is a really great open source SPICE, including graphical viewer. LeftDef is a very important format for SoC design. It represents what is underneath in terms of the layers, but it only shows the layers that are necessary for the SoC design. So things that are very important for routing, such as a route layer or a contact, which is sometimes called a cut layer. And these formats are used pretty extensively because it's a very easy format to use. It's text. Most EDA tools will use them, including the ones that we have in our flow. And it provides really an abstract information on the cells. You can see an example one here for a full adder. And we extract left views for all our designs so that they're easy to use and all provided. Also, in addition to the left files, we all provide lib files, which are originally from the Liberty engine, sometimes called the Liberty timing format. And it's a file format used for timing models contained in cell delays. It holds transition times, setup, hold, has logical cell functions, it has area, it also has power information. So we provide all that within the characterization of our cell sets. All the scripts are provided that give those values out. And it's entirely text-based. And again, it's also used similar to Left for all EDA tools. All the libraries, again, are fully characterized with multiple corners, and they include scripts to help others in expanding the library if needed. All the lib files or the Liberty files are provided with CCS and ECSM Liberty type files, which are useful for power annotation, as well as back annotated VHDL and Verilog output as well. So you can use them to simulate design with an HDL, open HDL that's out there to see the delays that are associated with your whatever design you're making. Once the cells are fully characterized, the best way to test them is using them to implement an HDL design. So we have several HDL designs we actually provide, and we'll talk a little bit later about them. The Liberty timing files and left views are provided only as an abstract description, and then the cell behavior may change once it's implemented. The synthesis is used, and it's mainly used in literature to compare the results across different designs. And then we also have place and route scripts that will route the physical element of the design from synthesis, so they're more accurate and it shows greater the variance within regards to the initial parameters. So here's some exact outputs. This one's particular output. We've run thousands of these place and routes with our standard cells, tested them through simulation. This just is one output. Here's another output just showing some of the, for one particular net output, showing a path histogram for this particular slack. So all that information is provided to allow you to get a good place and route from your design that you have. And you can create any design you want, which is really amazing. So we rely on some commercial tools to help do some synthesis and place and route, but we're also really, really, I would say, enthusiastic about integrating OpenLANE. So OpenLANE is the e-fabless open source design flow. It's the cooperation with OpenLANE has been really leading to improvements in their design, and we provide all the scripts, hopefully, for the OpenLANE integration. And we've been testing ourselves through OpenLANE, and we have hope to have further cooperation, which leads us to these open source types of tools that allow anyone to do full idea to GDS. So again, it's an open source type of flow. We're excited to really completely switch over to open source tools as they become available, not just OpenLANE, but any tool that we're informed of. We've used many of them, and Magic has been such a great tool for us. Again, we use it at Oklahoma State for our teaching of our integrated circuit classes. And it's easy to teach students, but we also have that integrated within the PDK and the SoC design, so you can use that within your classes if you want, or just if you're a hobbyist and want to learn a little bit about it. It all supports open source flows. So one of the key elements of our library, which is more getting into the details of this, is the height of the cell. And the height of the cell really is contingent on how the routes go together. Taller cells will have transistors with larger widths, but it will result in higher speeds. If you have smaller cells, it'll be tightly compact, but you might not have enough room to route everything. So the taller cells that we originally designed with the 18 tracks allows us a lot of room for routing wires, and it lowers the congestion that we have. The cell height is measured in terms of the number of routing tracks of the lowest non-interconnect metal layer that we have. And we'll talk about that as we go. What we mean by a track is it's the smallest section of space that really can accommodate a drawn wire, and typically defined in terms of width and spacing design rules for that respective layer. Typically 9-track cells are common or standard. You can also have 12-track cells for high-speed designs, but small cells like 7T for really ultra high density designs. It's really a trade-off in terms of getting the place and route tools to actually work. So this shows an example of our 12-track setup that we've actually made. Note that although being only 12 tracks tall, the cell can only accommodate 9 routes between the power rails that are shown here. And the power rails take space on these tracks as well. Cells of different height provide a simple solution for trading that speed and area that we want. But really, when we do that tracks, we really can't mix them within the same design for whatever we're designing. So when we're designing our cells, we've designed them according to what the connection is between each contact. You can do 2 things for this, and we define that terminology as a pitch, which is the wires are spaced at different sizes. Now, there's 2 ways of doing that. You can do via to via or line to via. Line to via is a little shorter because it'll give a more compact and more congestion. So we've opted for initially the via to via type of a pitch for our design, but we hope to have another cell set maybe within the month that also has a line to via setting for the tracks, and that'll squeeze the actual number of tracks that are in that design. To simplify the place and route, we try to use alternating directions for our layers, if anyone's familiar with designing layout, and that really helps the whole layout process work. We use a horizontal, vertical, horizontal type of routing, and this on more advanced nodes, it's really common to see a little bit of an aberration from that. The first 2 metals are typically done horizontally in those very low feature sizes that you see, but we typically have a horizontal, vertical, horizontal type routing. Another important process of the routing is the creation of the grid. The grids are used to easily compute all the computations from contact to contact. So different layers with the same spacing direction will have different thicknesses and spacing, AKA different pitches. So we try to create that spacing between each of them so that they have an easy route between the different metal layers. So for example, a metal 3 to metal 1 might have 11 to 8 for both horizontal tracks, but would be on top of each other very seldomly because it's an odd ratio. So we want to try to create simple ratios for all our grids in our 12-track, 18-track system. And we try to use ratios like 1 to 1 and 1 to 2, 2 to 3, and 3 to 4 between adjacent types of layers or route layers so that they can connect together nicely. It's also desirable to have the tracks aligned, and that allows stacked vias. Stacked vias are connections between different metals above each other. If you've ever used SCMOS rules, some of those rules, especially for the higher level feature sizes don't have stacked vias, and it makes it more congested because you have to put the vias next to each other, and you have to create room for those vias. So we try to promote that within our Stine cell library. Also, we tried to make sure that all the pins are placed on the grid. That really reduces the routing efforts. We stagger them if possible so that you can reach them horizontally or vertically. And the power signals are routed through abutting each cell together to increase that density of our standard cell sets. The standard cells are also designed so that they can promote gaps between each of the cells, and we fill them in with something called a filler cell. A filler cell is a dummy cell that kind of makes sure that the rails go between each other. And all standard cells are integer multiples of the smallest filler cell that we have. And it's sort of the common divisor to avoid less wasted space. So one of the interesting things that we've tried to do, and I hope this makes sense, is the SkyWater 130nm PDK has 5 metal layers as shown in this great diagram. It also has one local interconnect layer, which is shown in the green layer on the bottom. And if you can look at this really closely, you can see the K values are different for each one. The metal layers are all aluminum, and the local interconnect layer is titanium nitride. So as can be seen on this diagram, the local interconnect layer, or the Li layer, is much, much thinner than the other metal layers. And so the local interconnect has about 100 times more resistance per square area than metal 1. So this is a real big problem because the Li1 or local interconnect sits between what we call the forward end of line layers, that's below the transistor level at the bottom. We also have the back end of line, which is most of the routing wires. And so if we can use that well, we can free up metal 1 for routing. So we have a little diagram to show how we engineered that. So what we did initially is we tried to create avoiding using the local interconnect layers, except for local connections on the cells. As previously mentioned, the titanium nitride layer has much more resistivity than the aluminum layers. So the decision was made to provide all cell input and output names on metal 1 and prevent routing on Li1, even though you can do that within the cell, but we take care of that in and out to not block any of the metal 1 tracks. And we do that with a left file, and you can see that below. We've commented out the routing layer for the local interconnect and made it a master slice, which means to avoid it as it's using within the standard cell sets. So this shows an example of one of our standard cells. It's a full adder, and it has 3 inputs and 3 outputs. This is a total 6 pins on each. And you can kind of not see it really well on this diagram, but if I go to the next slide, remove all the lower level information, you can see the routing wires for the metal 1 tracks. And since all the pins block a metal 1 routing track, it's really easy to connect things together. We don't have to use high resistance Li1, and you'll see that it definitely when we show the results later in the presentation, not far away. So this is from the SkyWater 130nm flip-flop. It's a set reset flip-flop. You can see that highlighted below the local interconnect. And so that's a long and high resistant meander wire that's shown here. And so we try to avoid that within our design for pins. And you can see that here because the metal 1 has 100 times less resistance than the local interconnect. And so we try to engineer that into our standard cells to make them more efficient. So again, the inner cell routing is also extremely important. And because we do the metal 1 pins, this allows us to easily guarantee that other tracks are available for top level routing. And you can see an example from a standard cell route that we have here, and all the metal 1 tracks going nicely across. There's less routing congestion, and it's able to draw long and straight wires that allows an easy connection and very efficient design, and as you'll see, very high speed. So one of the other advantages of our cell set is we have well and substrate contacts. So the pre-existing SkyWater standard cells do not have them. And so you need specialized tap cells to place alongside of the standard cells in a design. And our cells offer a thicker power rail also with built-in well and substrate taps. And you can see the substrate taps here and the well taps here. And it really provides an easier way to connect to the body of the transistor, which minimizes the impact of the body effect, which is a very important element that happens within the surface of our semiconductor, especially for MOS devices. So this shows a couple of the cells in a table. There's a bunch of adders, full adders, 3 2 counters, 2 2 counters, which are full adders, half adders, AOI, OAI, NAND gates, NOR gates, muxes, tri-state buffers, inverters, normal buffers. We also have AND gates, a whole collection of flip-flops, asynchronous, and we hope to have synchronous too as well, OR gates. We also have antenna diodes integrated into our standard cell set, so you can integrate them automatically with your EDA tool, as well as decoupling capacitors and filler cells, as I mentioned before, as well as the ability to tie high or tie low for a specific set device. We currently have 62 cells, but we're expanding them even as we speak. We're currently only having devices that have standard voltage threshold. So we hope to expand out with multiple threshold like the SkyWater cells. Again, we used an 18 track or 6.6 micron, and our greatest common divisor of all our cells is about 110 nanometer, which is for the smallest filler cell. All the cell pins are exclusively on metal 1, as we mentioned before, and this really allows us to forbid routing on LI1, makes it more efficient. The well and substrate taps are included in every cell, and there's 0.6 micron power rails, which are really 3.6 times the minimum width on the local interconnect, and that really helps with electromigration. This is doubled on top of that with 0.61 micron power rails, which are 4.4 times the minimum width for the metal 1. Our base cell set has been published. It's freely open. Listed here, as I mentioned before, everything is included. All the characterization scripts, all the libraries, all the left files, all the lib files, all the Verilog and HDL files, they're all listed here for you to use. And we really pride ourselves on trying to be open and give you as much that we can to this library. We also have a 15-track and 12-track sets. We've already laid them out. They're just going characterization. And that really takes a really long time. Characterization is involved in taking the library and running it through a SPICE simulation for all the SPICE decks. And for our library, it can take up just 150 hours, just of unsupervised runtime for a single computer without, for one specific corner. So we're going to publish them listed here. And again, we hope to be 1 to 2 weeks, we'll have those out. And those have more track cells, they'll be smaller and more density. We also have future goals, and we hope to expand the cell set. We have 27 cells that we have removed for right now, but we're going to add them back. We're designing new and improved cells. We want to have low VT and high VT cells in there, and the low VT is for high power or high speed and high power, but the high VT is for low speed, low power. We're experimenting, as I mentioned earlier, with the line to via pitch, and that will reduce the track size by, we estimate, around 20%. We're also going to create an IO pad structure for bond pads that'll have electrostatic discharge or ESD protected, integrated within the bond pad, as well as different output current strengths that can be provided for whatever you want. We have examples, Verilog files, test benches, design flow scripts, all is included in our scripts. If you can't find it, just let us know and we'll help you as much as we can. There's also the pre-existing SkyWater standard cell kits. We have several versions, as I mentioned before, high density, high voltage. Most of these sets are around 150 cells, and they're just not standard VT sets, as we mentioned earlier. They're low VT and high VT, but there's a lot smaller. They're 9 tracks or 3.3 micron. The greatest common divisor of all the cells is about the same as ours, which is 110 nanometer, and the cell pins are not on just metal one, but they're also on Li one, which does cause some problems. The well and substrate cells don't have to be placed separately, and the power rails are not very thick. So you can see the local interconnect is only 1 times the minimum width, whereas the metal one is 3.5. We also will provide design flow scripts for the SkyWater standard cells, so you can use those to route whatever you want in the standard cell design. So you can use either, whatever you want. So we were really interested. Hey, we got these cells. We really put a lot of effort into them. We wanted to compare them. So we've done a lot of work in designing different types of RISC-V architectures. We've designed a single cycle processor as well as a pipeline processor. We have a full RV32i with different things in it. We have multipliers, floating point units, and we hope to put those also out on the library as well. The synthesis was performed using design compiler, DC, and we set it at 2 nanoseconds. We used the Innovis for the least of the place and route, and we tried to place them by choosing between 1 to 1.5 times the passing period on the synthesis. We did 6 iterations on the cell library, as well as the methodology used for the comparison is consistent across each cell library. So for our single cell RV32Is, this is just for one particular comparison. We show the different libraries. The first one is ours, and shows some of the other ones too. And you can see these two are ours, and then these are the SkyWater cells. We just have basically regular VT type sets for our standard cells. So look at the results that we have here. So even though our cells are a lot taller, they're 18 tracks, okay? So you can see the area is a lot larger, but it's not double what you would normally see, right? Because remember that these SkyWater cells are 9x. Also notice that the speed, we got 327 megahertz out of our place and route synthesis. And that's fastest of all the actual synthesis. You can see area and power delay product values that are listed here. And we have good correlation between our synthesis and our frequency through place and route, and from synthesis to place and route. So we really have a good set of standard cells that really produce really great. So again, our high-speed cells are best compared to the SkyWater cells and our medium speed cells in the SkyWater set. And the main advantage that we have is we ban the Li1 for the inter-cell routing. And really that impacts wire delay. As anyone who is familiar with this area, we know that below 180 nanometer wire delay is the most prevalent element of delay. So this really pays dividends down the road. And so although our 18 tracks, as I mentioned before, are twice as tall as the 9T ones, we only have 63% larger on the place and route. And that's really makes us believe that the 9T cells that we have. Now, again, remember that our cells are only standard VT. So we believe that once we change to a lower VT, that we'll get higher speeds out of our cell set, much more efficiency. And we feel that they're very competitive with the SkyWater cell sets. And again, everything is included, all the characterization, all the testing, it's all included. And again, it's, we're still working to put out more every day. We will put out the different tracks that we mentioned before. These shorter cells will have hopefully more closely aligned with the SkyWater cells. And hopefully we'll see some of the estimates as we do that. And we'll publish all that information for you to see as we go forward. So the Git repository containing all our source files and full flow is published here at the following URL. Again, that was presented earlier. We provide a complete standard cell library and system on chip design flow that helps the community. And we provide everything. We provide all the source files, all the scripts, all the testing, all the test benches, all the Verilog files. We provide all in the repository. And we're really welcome any kind of questions on the Slack channel or via email if you're interested in contacting us about what we've done or why we've done this. We're always open to new ideas and what we can do and how we can improve it. And I'd be amiss if I didn't really give a shout out to all the people that have really encouraged and supported this project. Tim Ansel from Google, Mohammed Qassam and Tim Edwards, who've been really instrumental in pushing this go, as well as SkyWater technology people and colleagues and others from this initiative. They've been really extremely helpful. We've also been really, I would say, improved from all the people that have helped us along the way. They've helped us teach and mentor us to really provide a better standard cell set, as well as design these design flows, as well as tape out stuff to silicon. So we understand the full process from idea to GDS. And then also wanted to thank all my Oklahoma State colleagues and administration who are really very supportive in getting this initiative to move forward. So I really appreciate your opportunity to listen, and I welcome any questions that maybe that Stefan has or anybody else. I'm open to anything. Again, you don't have to ask a question now. You can always ask a question later on Slack or whenever. I'm always open, and I really I love this area, and I really want to help people see what magic you can do. You can create actual silicon with all these things that we've created. So thank you very much.
Thank you very much. I really enjoyed it. I was muted for a second.
No.
So there came a couple of questions. One was all right, like at the beginning, I think. I think it was answered, but maybe you can repeat. What is the most current device library for this PDK? Is it still S8, PH, IRS, 10R?
Okay, let's see if I can. Sorry if this is, I'm flashing the screen here. I'll try to intermix it with slower. I don't have any music for you, so.
Oh, yeah, mine is turned off already.
Yeah, I was going to sing everyone a song, but is this one?
Yes, I think that's probably it, right?
So this is the SkyWater 130nm PDK. It comes with standard cell kits, and these are the current ones. And we also have, like I mentioned before, we'll have design flows so that you can use these in commercial and OpenLANE and those kinds of EDA tools.
So, and you spoke a lot about the cell height,
yes,
and how you chose for higher.
Yep.
So what's the trade-off there? Maybe you can repeat. There was some discussion, and maybe people were arguing about pros and cons of.
Yeah, there's a lot of pros and cons. I mean, the ultimate, I would say the ultimate rub there is that, you try to synthesize and place around, you can see the results. But the higher that you make it, the more wires you can fit in between the design, and the more complexity you can make in a standard cell set. And it also allows, like, especially if you have SoC, is not just one design. So you could have an analog design or anything else that needs to route over the chip. So if you have a very tight and dense type of cell, you might not be able to route across the chip because there's just not enough space. So that might limit other types of opportunities for adding different things, IoT, anything that you want to add different types of elements to the silicon. And again, all the PDKs there, you can make analog parts, you can make digital parts, put them all together, make a mixed signal, a high frequency, all there. And so these higher track heights really promote that connections. Now, what's the disadvantage? Of course, if you have more space and more wires going between them, it's bigger, so it might incur more power. But again, there's things you can do. You can turn off certain parts of your design. You could use different kinds of retention registers, things that in that regard. It's a really hard question to analyze without really going through. But we try to create lots of different avenues for you. And again, we're coming out with new tracks within the week.
Okay.
So
great
question. That's a really great question.
So that's like probably when you once you started, you want to explore a little bit the advantages, disadvantages using tools.
Yeah. But it's all here. You all can do it, and you could get all the tools and try them. And then hopefully, get really excited, especially when Matt Goodhouse talks about memory. You can put memory along with this. It's really exciting. Maybe I'm just getting all too excited about it.
No, I think that's the right amount of excitement.
Yeah.
So I'm wondering, did you like already created tape out with it? Like, did you already receive it back?
I
Totally completed?
I know that we have taped out with these standard cells, so they have been thrown through. I don't think they're back yet. I thought maybe it was like November or something like that, but we have gone through tape out on the cells to use them. And again, we've used all our experience in taping out over the years. We've done lots and lots of chips, again, all the way down to 14 nanometer.
Nice,
That's a
interesting.
challenge. 14 nanometer is really a challenge, as
And,
my students will tell you.
and so when you receive it back, will there be like some verification phase where you will like check?
Yeah, definitely. We hope to get the chips back and then test them with our probe card. We hope to get a probe card and then test these chips. We're very confident based on our experience in designing cell sets. Like I said, I've done a lot of cell sets on libraries before, along with my great students. They're really just fantastic. And so we really think that we are going to get something back that's going to be working. And again, we've gone through tape out. So
Oh, yeah, that's
great
really.
question. And also another great question.
So I'm wondering, like, how long does it take for you? Like, so you have a lot of experience, and like, arguably, like 130 nanometers is not like the bleeding edge where you have to probably go the full stretch of your experience, right? But how long does it take you if you say like, okay, it's another week until the next one is released? So you and
Yeah, well,
you say like in man
I
hours?
yeah, I've been very fortunate. The real first you have to like design all the cell sets. And I think one of the advantages of doing this area, thanks to all the innovations of PCs and computing, is the ability to do these things more efficiently. And so we use scripts a lot to really help speed up this process.
Mm-hmm.
Unfortunately, you still have to wait for characterization, which seems to be more of the bottleneck for getting these things out. But we do know how to do them really quickly now. I think somebody who was doing this could probably do a good standard, like in addition to the standard cells, probably in maybe like a good 2 to 4 weeks, easy. We're a lot more experienced, so it takes us a lot quicker to do it.
Okay.
And we've done very many iterations over these cells. And again, I'm very fortunate. I have all my great students. They're just
Mm-hmm.
they've learned quickly. They're like sponges. So I've been able to teach them how to do it and learn, and they've been just really fantastic.
Interesting. So, and how does characterization work? Is it true? Like it's pretty manual still.
Okay, yeah. So characterization is basically spice runs. So what you have to do is you have to run a spice run for every cell for different parameters, and you have to figure out based on the function what like for example the delay, right? So if you're going to do a delay of an AND gate, you give both inputs a 1, and then you toggle one of the inputs to see the output go back and forth. So you have to do that, and then you also have to calculate capacitance, power dissipation, all these elements that are really essential to each cell. And so for one specific cell, you may have hundreds of spice runs that are done for that characterization. And that makes it, you can see, we estimate about 150 hours for each corner
Mm-hmm.
just to run it on and we design all our servers by hand just because we find that we get much better performance doing that.
Interesting. Yeah. So,
Yeah.
yeah, which kind of tools do you use for characterization?
So for right now, like when I first started doing this, which is eons ago, I wrote my own scripts, and it was really difficult. I wrote them in Perl, and today we use, like for right now, we use Liberate, which is from Cadence Design Systems, but we also hope to have our own characterization tool in Python soon, so that people can also run it there. It might be a little slower because Cadence has more engineers that they can work on stuff. But we provide all those scripts for you.
Mm-hmm.
And then also you can ask questions if you have, like, how did you do that? Or how did you do this? We really want to share.
Yeah, I think you made it really clear that people should just get in touch with you if they have any questions. That's
Well,
good.
yeah, but it's what's really fantastic if you think about this is that, you know, I know 130 nanometer is not 14 nanometer. It's
Yeah.
not 10 nanometer. It's not 5. But the power of ingenuity of what you can do and what you put on silicon can now be done by anyone. And so I think those are the best innovations that come out, is when people have great ideas. It doesn't matter where you are. You could be a hobbyist, right? And you could say, oh, I want to definitely implement this. I think it's going to be great, and put it on silicon, and it could be the next, I would say tickling Elmo or something like that.
Yeah,
I'm showing my age here. That was the really hot thing when I was younger. So
yeah, I think that's really great. I think that's one of the great opportunities that we have nowadays. Like people like me who are kind of in academia but never really did it, like don't have the steep learning curve, don't have all the tools that you need, all the contracts you have to sign to even start, right? And I think that's really great. And
and
there's one
it's
question in this direction. Like someone asked if there's like courses, like online courses you might have available on the design process. I think
I
that.
am definitely thinking that we might have it eventually a course on standard cell design, just on the more intricate elements.
Mhm.
And I'm definitely open to doing that. Again, I really love to share what we've learned over the long years of doing this. And again, I didn't just do this myself. There were people that taught me how to do this. Many talented engineers from the Silicon Valley area who just spent time with me learning how to do that and this. So yeah, I'd love to. Yeah,
Yeah,
that'd
so
be
there's
great.
people in the chat now saying like they would really appreciate like this kind of
Yeah,
course, especially from you. That's really great.
yeah, I'd love to. This is great. I mean, it's like these standard cells are really what makes things like cell phones and things work today, because you can design these quickly.
Yeah,
Custom design is still important, as well as analog and high frequency things. So you can still integrate them together, but you can do these things more quickly in digital with system on chip design, and the possibilities are really endless.
yeah.
Which is just, that's why I got into this area to begin with, just because it's so exciting. I think it's exciting, but my wife doesn't think it's so exciting, but I think it's so exciting.
I think everyone on this presentation agrees it's really exciting. And it's
Yeah.
also a technical question. Speaking about exciting, people are excited about the track height, right? Do the definitions allow you to combine the 18T and 9T process?
Okay, that's a really fantastic question. Because the height is related to the power rail,
Hmm.
as you put them next to each other, they won't fit, right? But there's nothing saying you can't do a 9T on the left and then doing a 18T on the right, and then connecting them together with some routing. So
Yeah.
you could do it that, but you can't really mix them because the cell height, the rails have to connect to each other. It's a really fantastic question.
So it's not, you can't combine them arbitrarily, but on a
Yeah.
causal granularity you can do this.
Yeah, definitely. There's nothing wrong with doing that. I think that'd be wonderful.
Interesting, yes. Um, so I think you already said a little bit about it. People can get involved. Like, but what are your most urgent needs at the moment? Where would you encourage people to get involved? Like, is it like picking up one of the libraries that you have on your roadmap, or is it like characterization work? Is it
Well, that's a
testing
great question
something? Yeah.
too, as well. I mean, you got a ton of great questions, so it's thanks to the viewers. But I think one of the definite things that we could definitely use is that there are so many little intricate or number of possibilities or probabilities of, I would say, little things that you can tweak. For example, using the standard cells with the different tools, that we can't really catch them all. We can't really catch like all the errors. So taking these and trying to run them through a design, and either through synthesis or place and route, just to see if there's any issues that come up. Those would be really, I think that's a really high need
Hmm.
in trying things, because we really can't test all the possibilities of these tools. There's so many arguments. And so that's one of the great things about open source. I think that's what really makes it really wonderful, is that you can use all the great talent that's out there to really, massage things and see what works and what doesn't work, as
Hmm.
well as new designs too. I think that'd be great too. Like, hey, I designed this new IoT device or this new processor, and we did it in 130 nanometer PK, and it beats Intel. Sorry.
Yeah, I'm looking forward to this to the first round of
That's,
designs. So
yeah,
we're thrilling.
we are too. We are too. We're really excited. We're always excited. That's I have to. You
Awesome.
know.
Yeah, so I think those were the questions. I didn't see any more popping up now.
Okay.
Thank you very much. I really enjoyed it. It was halfway lecture for me because I actually never learned it. So now I feel more educated. I learned a lot during the presentation. I think I I can follow the next one too, hopefully, the OpenRAM one with Matt.
Sounds good.
So thank
Yeah,
you.
and like I said, yeah, any further questions, feel free to contact us. We'll be happy to help as much as we can.
Yeah. Thanks everyone for
And
attending.
thank you very much.
Yeah, it was really great.
Thank
Thanks a
you.
lot, James, for presenting. The next one will be Matt Goodhouse talking about OpenRAM. Yeah, you can watch the other videos on YouTube. Subscribe to our channel, please. We just passed the 2,000 subscribers now, which is great. Yeah, so see you again. It will be end of October. And enjoy your time. Have a great day. Have a great evening. And see you soon. Bye. Bye, James.
See ya.
Bye.
Do the wave.